When a satellite leaves the Earth, its launch vehicle follows an extremely accurate path, delivering its payload to a precise orbit. Probes may be heading away from Earth to other planets or to interstellar space, but wherever a spacecraft is targeted, its course must be calculated with exquisite precision, and it must be monitored and adjusted regularly. The story of modern science is linked to humanity's understanding of the sun and the planets, and the way they move. Newton, building on the work of Copernicus, Kepler, and Galileo, was able to demonstrate mathematically the orbits that the planets followed. The sun and the planets did not orbit the Earth, and orbits were generally elliptical rather than circular. Using the newly developed calculus, astronomers were now able to accurately predict eclipses and transits. In 1772, Lagrange predicted that smaller bodies could be trapped at very precise locations near much larger planets. More than 100 years later, Trojan asteroids were discovered sharing Jupiter's orbit. In the 19th and early 20th century, several mathematicians had calculated exactly how fast a body would have to travel to break free of the Earth's gravity and go into orbit. But these were exercises in theory. At the end of the Second World War, both the Soviet Union and America had salvaged what they could of the remaining German V-2 rockets and began duplicating the technology. The V-2 had a range of around 300 kilometers, and it followed a ballistic trajectory. But military leaders wanted greater range. A team from California's Jet Propulsion Laboratory had been commissioned by the U.S. Army to repurpose a small scientific rocket as a battlefield weapon. At this time, the Army was thinking of missiles as a new type of artillery, but JPL's liquid-fueled WAC Corporal proved impractical for field use. In 1948, Major General Holger Toftoy, a driving force behind the American V-2 program, decided that the big German rocket could be tipped by the smaller WAC Corporal to make the first two-stage rocket. Known as the Bumper program, it launched 8 rockets with mixed success. There were problems getting the upper stage to fire, yet when everything worked, it set a new altitude record of 400 kilometers. Just like the Americans, the Russians began by mastering the V-2 and then scaling it up. The R-1 and R-2 missiles were stretched versions of the V-2. The Soviets were also experimenting with multiple stages. The R-7 was designed to carry a nuclear warhead. The difficulties associated with igniting a second stage in flight were eliminated by clustering 4 boosters around a core stage, with all engines igniting on the ground. It began testing in 1957, but problems with the boosters had to be corrected before a successful launch in August 1957. In the early 1950s, America's long-range nuclear capability relied on Air Force bombers like the B-36 and the B-52. The Army had focused on short-range weaponry, but their V-2 team, now working in the Army Ballistic Missile Agency, had developed the intermediate-range Redstone missile.
Mission start.
Though it was much smaller than the Soviets' R-7, it too was designed for a nuclear warhead. The US Navy was also developing a rocket, not as a weapon, but for purely research purposes. Known as Vanguard, it used an Araby second stage and a Viking lower stage. Because it had no military application, this rocket was favored by US President Eisenhower to carry a satellite to orbit as part of the International Geophysical Year. Since 1955, Eisenhower had called for an open skies policy, where reconnaissance aircraft could freely collect information about an adversary's military installations. This had been flatly rejected by Soviet leader Nikita Khrushchev. Concern in the US administration was that the Russians would regard the overflight of satellites in the same way as aircraft. Then came a surprise. Although the Soviet Union had also declared its intention to launch a satellite for the International Geophysical Year, few in the United States had taken this seriously. On October 4th, 1957, the Russians launched the first artificial satellite. It was an 83-kilogram sphere called Sputnik. Its purpose was to prove that it could be done. Its distinctive beeping was easily picked up by amateur radio operators. Sputnik was meant to fly in a highly elliptical orbit, but a fuel regulator had malfunctioned. It was not the flight path intended, but this was of little significance as long as people around the world could hear it. The only data it returned was via the duration of the beeps, coded to indicate temperature and pressure within its sphere. While its 83-kilogram mass was much heavier than the Americans could launch, its components were heavy too. Sputnik's dual radio transmitters relied on power-hungry vacuum tubes, which needed a cooling fan and 3 bulky silver-zinc batteries. Its orbit, inclined at 65 degrees to the equator, took it across the world's populated areas, including the United States. Americans were stunned that the Soviet Union had the ability to orbit a spacecraft, and they expected their government to respond.
President Eisenhower reassures the nation that Russia's success with the first satellite does not indicate a serious lag in American rocket research.
I consider our country's satellite program to be well designed and properly scheduled to achieve the scientific purposes for which it was initiated. We are, therefore, carrying the program forward in keeping with our arrangements with the international scientific community. Vanguard, for the reasons indicated, has not had equal priority with that accorded our ballistic missile work.
Eisenhower invited the non-military Vanguard team to launch America's first satellite, completely sidelining the more advanced Redstone program. Working with JPL, the US Army had added solid-fueled upper stages to the Redstone to boost a warhead beyond the atmosphere. Called Project Orbiter, both the Army and JPL understood that this tested configuration could easily reach orbit. JPL was, and remains, a branch of Caltech, the California Institute of Technology. Their team had far more enthusiasm for scientific research than it did for weaponry. And without authorization, they quietly designed and built a research satellite. But the next orbital flight was again made by Russia, with a dog called Laika. Sputnik 2 was a much larger craft. It had a life support system and an array of monitoring instruments. It launched on an improved version of the R-7 in November 1957. Unfortunately, Laika died when her capsule overheated after several orbits. After the second unmatched Russian spaceflight, there was more jubilation across the Soviet Union. But Americans were getting impatient with their president's response.
The mere fact of this being orbit involved no new discovery to science. They knew it could be done. At least they say so, and they have for a long time. So that's no new discovery. So in itself, it imposes no additional threat to the United States. Thank you.
Finally, in December 1957, Vanguard had its chance, and Americans were watching it live.
Stand by.
Test Vehicle 3 was a spherical satellite weighing less than 2 kilograms. It was transistorized and designed to return data about its thermal behavior.
2, 1. Ignition. Liftoff.
It was a humiliation, and it heightened fears within the American public that they were technically inferior and vulnerable. Almost immediately, the Redstone Group was authorized to launch a satellite, and they were given just 90 days to achieve it. The rocket, now called the Jupiter C, was guided, while the upper stages, built by JPL and known as the tub, had no independent guidance system. After the tub separated, it would rely upon spin to continue along its line. The satellite, named Explorer 1, was equipped to investigate the radiation environment beyond the atmosphere, and it was able to register impacts from micrometeors. Physicist James Van Allen had been working with sounding rockets and was keen to provide an experimental package to go into orbit. Early in 1958, the Jupiter C was being readied. All military personnel associated with the mission remained at Cape Canaveral.
3, 2, 1. Fire command. Fire command.
The launch was perfect. 8 minutes later, Explorer 1 reached orbit, but at the time, no one knew. At the designated time, there was no sign of the satellite. Its orbit was far more eccentric than intended. Like the Russian craft before it, departures from the expected flight path were of minor importance. The fact that the satellite was in orbit was enough. Initially, readings from Explorer's Geiger counter seemed random, until it was understood that they varied with altitude. James Van Allen realized that concentrations of radiation encircled the Earth. They were named the Van Allen belts, and the orbital anomalies of Explorer 1 had significantly aided their discovery. A successful American launch to orbit marked the end of the first round in what was already being called the space race, a competition fueled by mutual distrust and fears of nuclear attack. In the US, a crash program to match the Soviet R-7 was already underway. The Atlas concept began testing in 1957. Its lightweight propellant tanks were also the rocket's outer skin. It needed pressure in the tanks to stop it from collapsing. At the time, US leaders talked about the missile gap, an overwhelming belief that democratic America was far behind its communist adversary. While it was clear that the Soviet Union had an advantage in heavy lift capability, it was less obvious that the US had far more advanced electronics and much deeper pockets. It took time to perfect the Atlas, but eventually it was deployed with nuclear capability. But its liquid fuel gave it the same drawbacks as Russia's R-7. In 1958, NASA, the civilian space agency, was established, rapidly recruiting 7 test pilots for its manned spaceflight program. Instantly, these men, now called astronauts, were front-page news. The same year, the Soviet space effort recruited 20 cosmonauts, but this was a more secret exercise. There were secret plans taking shape in the United States, too. President Eisenhower set up ARPA, the Advanced Research Projects Agency. Intended to push the boundaries of science for possible military applications, it was generously funded. Up until 1959, the United States succeeded with 25 satellites, with a further 17 failures. Most of America's successful flights were made by early spy satellites as part of the Corona program, which received very little publicity. In the same period, the Soviet Union successfully launched 5 satellites. In 1960, President Eisenhower accelerated the Corona program, developing surveillance satellites. They were called Discoverer missions, pretending to be scientific investigators. The true nature of the Corona program remained secret until 1992. A collaboration between the U.S. Air Force and the CIA, 5 series of these satellites with a KH designation were developed. They were the first spacecraft to have stabilization in 3 axes rather than being spin stabilized or just tumbling aimlessly. The later series had an engine that could be restarted in orbit. Launched from the Vandenberg Air Force Base in California, they were the first satellites to be put into north-south or polar orbits. A set of rules emerged for launching to Earth orbit. They were prompted by the rigid laws of physics and concern about the neighbors. A launch site close to the equator allowed the rocket to benefit from the Earth's rotation if it was launched to the east. The Soviet Union chose a site at Tyuratam, in a sparsely populated region of Kazakhstan, 46 degrees north of the equator, that is now known as the Baikonur Cosmodrome. The United States adapted the Atlantic Missile Range at Cape Canaveral, Florida, just 28 degrees north of the equator. Both of these sites remain in use today. Gimbaling engine bells allow a rocket to follow a precise course, yet the path to orbit is complex. It will differ according to the intended orbit, the type of launcher, and the kind of payload. Initially, a launcher will rise vertically to clear the denser regions of the atmosphere and reduce drag before it begins to pitch over. Pitching in an easterly direction will save on fuel. However, other factors must be considered. Following a due east heading will only result in a due east orbit if a rocket launches from the equator. Otherwise, it will follow a path that has the center of the Earth as its focus, and its angle to the equator will be the same as the degree of latitude of its launching point. Launching due east from Cape Canaveral sees the rocket heading southeast over island nations. It is not acceptable to drop stages along this line. By launching from the Cape on a more northerly course, a rocket will have nothing but ocean below it until well after its payload has reached orbit. From Baikonur, Russian rockets have a narrower northeasterly path above wilderness that they must follow. An orbital incline of 51.5 degrees is standard for orbits launched from this site. There are designated drop zones for the stages that are kept clear at launch times. Since the breakup of the Soviet Union, Russia has had to lease this site from the Kazakh government. In the 1970s, both Russia and America became interested in orbiting space stations. The US with Skylab and Russia with a series of Salyut missions. Lack of funding soon put an end to Skylab, but the Russians continued accruing experience in long-duration space missions. In 1986, the Soviet Union launched the first piece of the Mir space station, and the first crew took up residence a month later. New modules continued to be ferried to orbit on the heavy-lift Proton rocket. In 1988, the European Space Agency began collaborating with the Soviet Space Agency, starting with French cosmonaut Jean-Loup Chrétien, arriving for a 22-day sojourn in November. NASA had plans for its own space station. One of the primary design requirements of the space shuttle was the lifting and assembling of an orbiting research platform. The concept became known as Space Station Freedom. But again, US politicians would not release the funds. The Soviets also had plans for a bigger, better Mir 2 and had begun building modules. But after the dissolution of the Soviet Union, the new Russian Federation had its own budgetary problems. In 1994, NASA saw an opportunity and began working with the Mir program. A port was fitted to Mir to allow the shuttle to dock. Russian cosmonauts began riding to orbit on the shuttle, and American astronauts began working on board Mir. The United States began learning about building and maintaining a long-term presence in space, and the extra funding allowed Russia to continue its Mir program. In 1997, a Progress cargo craft collided with the space station, raising concerns about safety aboard Mir, and NASA and Roscosmos began looking to a replacement space station. Mir limped on for a further 2 years before it was deorbited. It had been continuously occupied for close to 10 years. Late in 1998, a Proton launcher was being prepared to deliver the first piece of a new space station. It was called Zarya. The Zarya and Zvezda modules, originally intended for the Mir 2, would form the nucleus of what was now known as the International Space Station, a collaboration between the United States, Russia, Europe, Japan, and Canada. Finally, the space shuttle would be used to its full potential, but there was a problem. While the shuttle had visited Mir in the same orbital plane as the core module of the new space station, it had not ferried anything like the very heavy components to this particular orbit. For the shuttle, being launched from the Kennedy Space Center, it required a much more northerly launch azimuth to reach the steeper orbit. This meant more fuel and less cargo. Only the later versions of the shuttle were light enough for missions to the ISS, and improvements to the engines meant that, when carrying a meaningful load, this orbit was just feasible. The launch window was much narrower for these missions, with launch times being limited to just 5 minutes when the shuttle was able to make the correct orbit.
Position on course for a 51.6 degree, 136.36 statute mile orbit.
To achieve rendezvous, the shuttle had to lift off when its launch site crossed the orbital plane of the space station.
Three main engines on it and have now been throttled down to 72% of rated thrust or atmosphere.
Usually, rendezvous and docking would happen 2 days after launch. While the mathematics associated with this complex maneuver had long been mastered, the practicalities of getting a spacecraft to perform to the required precision were pioneered in the Gemini program. By 1965, the US was squarely on track for a moon landing, and Gemini was tasked with perfecting orbital rendezvous and docking. Given that early satellites often missed their expected orbits by as much as 100 kilometers, rendezvous was seen as a challenge. Future moon missions would require rendezvous in lunar orbit. The new Gemini capsule was equipped with maneuvering thrusters controlled by the crew via an onboard computer. Astronauts rode to orbit on a refinement of the Titan II missile. On Gemini 4, the second manned Gemini mission, astronauts Ed White and James McDivitt attempted to approach the spent upper stage of their Titan launcher. Both were experienced test pilots, but by thrusting toward their target, they found it became more distant. The complexities of orbital mechanics required a different approach. As the Gemini program progressed, missions were planned that would see the launch of Agena target vehicles equipped with docking collars. Crews spent long hours in a variety of simulators practicing docking maneuvers. The nose of the Gemini craft could lock into the Agena, and the crew could control both craft. Gemini 6 astronauts Wally Schirra and Tom Stafford would be the first to attempt to rendezvous with the Agena. This would be a dual launch, with the Agena lifting off slightly more than an hour before Gemini 6. While the astronauts were being strapped into their capsule, launch control was entering the final stages of the countdown for the Agena. It would launch to a 298-kilometer circular orbit. As it passed above the launch site after its first orbit, the Gemini spacecraft would launch to a lower orbit. At least that was the plan. Without a target, the mission was scrubbed while NASA decided what to do next. A replacement Agena would not be ready for months, and NASA was in a hurry. The next scheduled mission, Gemini 7, was intended to be a long-duration exercise with astronauts Frank Borman and Jim Lovell orbiting for 2 weeks. This flight would continue as planned, but several days after their liftoff, Schirra and Stafford, in what was now called Gemini 6A, would launch and attempt a rendezvous.
Ignition.
On December 4th, 1965, the Gemini 7 astronauts began their marathon flight. Gemini 6A would launch from the same pad, and technicians had only 9 days to prepare for its launch. The following day, a new Titan II was moved into place, and engineers began working around the clock, readying it for flight. Work proceeded well, and the spacecraft was ready for launch on December 12th at 9:54, just 27 seconds before Gemini 7 passed overhead. For the rendezvous, Gemini 6A would be the active craft, making all the orbital changes, while Gemini 7 continued along its predictable path. 6A would take a lower circular orbit and catch up on its target from behind. Gemini 6A made a perfect launch. In less than 6 hours on Gemini 6A's 4th orbit, the two spacecraft were beside each other. Future Gemini missions would perfect more complex and rapid rendezvous techniques, but the first ever space rendezvous was a huge advance in orbital practice. Today, rendezvous is a routine part of spaceflight. The International Space Station relies upon visiting craft to replenish supplies or to exchange crew members. The Sentinel-1A satellite was delivered to a sun-synchronous orbit in April 2014. This is a precise polar orbit 693 kilometers above the surface that takes advantage of a slight bulge at the Earth's equator to drag its orbital plane to the east by about 1 degree per day. Its job is to observe changes in sea ice, changes in land use, and movement in the Earth's surface, and its unique orbit contributes to the accuracy of its measurements. It always passes above the same point on the Earth's surface at the same local time. Its twin, Sentinel-1B, was delivered to this same orbit in 2016. The two Sentinels work in tandem, separated by 180 degrees. Their attitude control system ensures the craft holds steady to establish contact with the ground and for its solar panels to collect sunlight. Its orbital speed, and thus its altitude, is adjusted via the satellite's own propulsion system. Even when it's following an accurate path, its orbit requires regular adjustment by operational staff on the ground. Irregularities in the Earth's gravitation, the influence of the Sun and Moon's gravitation, and solar radiation pressure are random forces that will make a satellite drift. Being in a north-south orbit, the Sentinel satellites communicate via the Polar Communication Outpost in Svalbard. Signals are relayed to the European Space Operations Center in Darmstadt, and operational commands are sent via a return loop. A satellite's lifespan is an estimate of how long its fuel will last, and judicious use of a spacecraft's propulsion and attitude control systems can greatly extend a satellite's life. One spacecraft that has no propulsion system at all is the Hubble Space Telescope. The telescope's precision optics would be contaminated by thruster emissions. To control its attitude, Hubble uses electrically powered inertia wheels. It can point with an extremely high degree of accuracy. At an altitude of 340 kilometers, its orbital decay is minimal. When Hubble was visited by the Space Shuttle for regular servicing, its orbit would receive a boost. With the end of those missions, it has been losing height, but it's difficult to predict when it will re-enter the Earth's atmosphere. Launching a satellite from the European spaceport close to the equator in South America offers advantages for spacecraft that need to operate in geostationary orbit. When a rocket, launched from higher latitudes, needs to deliver its payload to geostationary orbit, it must use extra fuel to change its orbital plane. Geostationary satellites are released into an elliptical transfer orbit. The satellite's own propulsion is then used to circularize the orbit at 35,786 kilometers. Communications and weather satellites in geostationary orbit appear to be fixed in the sky. They orbit above the equator at the same rate as the Earth's rotation. Ground stations do not need to follow a moving target, which is a huge cost saving for commercial communications operators. As a satellite nears the end of its life, it must retain enough fuel to lift it out of this crucial orbit to what is called a graveyard orbit, where it becomes space junk. Currently, there are 562 satellites in geostationary orbit, and it's getting crowded. While an interplanetary probe may not appear to orbit anything, it is still governed by the iron rules of orbital mechanics. In August and September of 1977, the two Voyager probes were launched. They were headed for the solar system's giant planets. Their Titan IIIe rockets were just powerful enough to send the craft to Jupiter. From there, they would rely on assistance from the planet's gravitation. Gravitational assist had only been done for the first time 3 years earlier when Mariner 10 used the gravitation of Venus for its flyby observations of Mercury. Timing of the Voyager missions was dictated by the peculiar planetary alignment that happened in 1977. It will not happen again till 2150. Trajectory designers studied 1,100 different paths their two probes could follow. While mission planners understood that it should be possible to fly past Jupiter, Saturn, Uranus, and Neptune, there was doubt that the spacecraft could survive what would be a 12-year journey. The two Voyager spacecraft were identical, but they were given different tasks. Voyager 1 was to focus on Jupiter and Saturn alone, with great stress from mission planners to observe Saturn's moon Titan. Voyager 2 would attempt a flypast of all 4 outer planets. The ambitious Grand Tour was at the limits of the technology of the day. Computers on the identical probes have less than 70 kilobytes of memory, the size of a modest JPEG file. Data is stored on an 8-track tape machine, and the central processor is around 8,000 times slower than today's smartphones. But JPL, the group that built Explorer 1, assembled the best spacecraft possible in the 1970s.
1, we have ignition, and we have liftoff. We have liftoff of the Titan Centaur, carrying the first of 2 Voyager spacecraft to extend manned senses farther into the solar system than ever before.
Voyager 2 launched first. It was on a slower path to Jupiter. Voyager 1, launched 2 weeks later, would pass its twin after 3 months. They went into heliocentric orbits at a speed relative to the Sun of close to 130,000 kilometers per hour. This highly elliptical trajectory would reach its high point somewhere between the orbits of Jupiter and Saturn. Without any other influences, the spacecraft would then begin falling back toward the Sun. The paths of both probes were timed to take them close to Jupiter, where the giant planet's gravitation would accelerate the spacecraft and put them on a new orbital path towards Saturn. Navigation in deep space was reliant on the Deep Space Network, not just for communication with the probes, but for accurate radio ranging assessment of their positions. During the latter phases of the mission, newer, more accurate methods evolved. Regular refinements of the Voyager's trajectories were made through course correction instructions, relayed to the craft, and then executed with precision timing via the onboard clock. In January 1979, Voyager 1 began sending back images of Jupiter. Mission specialists, who had been waiting for more than a year, were flooded with new information. Almost everything they saw was unexpected. It was thought that Jupiter's moons would be cold and cratered like our own moon, but each was unique. As Voyager 2, 3 months behind, was approaching Jupiter, trajectory specialists were able to retarget the spacecraft for closer scrutiny of the moons. Precisely timed nudges from the thrusters allowed the craft to make fine alterations to its flight path. When Voyager 1 was leaving Jupiter, the giant planet's gravitation had accelerated the craft by 36,000 kilometers per hour. At Saturn, researchers were stunned at the complexity of the planet and its ring system. The rings were more complex than imagined, and new moons were discovered. Voyager 1 then passed beneath Saturn and curved upward above the orbital plane of the planets, leaving the solar system. Voyager 2 arrived at Saturn 9 months after its twin. It would pass closer to the planet than Voyager 1, yet even from a distance of 1 million kilometers, detail within the rings was clear. It observed changes in the brief time since Voyager 1 had visited. The probe returned pictures of the moons Iapetus and Enceladus, as well as 17,000 other images of different parts of the Saturnian system. Then it swung behind the ring planet, losing contact with the Earth. When radio contact was re-established, the Voyager had increased its speed by 18,000 kilometers per hour, and it was headed for Uranus, It would take 4.5 years to get there. At Uranus, there were no swirling clouds, but Voyager 2 returned remarkable images of the planet's 5 major moons, particularly Miranda, which appears to have reformed after a shattering impact. The Voyager had discovered 11 unknown moons and 2 new rings, and it was now headed toward Neptune. In February 1988, a command was sent for the longest course correction of the mission. Still 18 months away from Neptune, Voyager 2 fired its thrusters for 2 hours and 33 minutes. It would allow mission scientists a close look at Triton. It is the only large moon in the solar system to orbit in the opposite direction to its planet's rotation, a retrograde orbit. In June 1989, the Voyager began its observations of Neptune. It has long, narrow clouds and winds that blow at 2,000 kilometers per hour. A dark spot, believed to be a storm, was observed. At closest approach, the probe flew over Neptune's north pole and began looping down toward Triton. After a journey of more than 12 years, Voyager 2 would capture images of the last body in the solar system. Here was a moon like no other. Rather than forming at the same time as Neptune, Triton must have been a wanderer, captured by the planet's gravitation. There were very few craters, and its surface features are diverse and relatively young. As researchers pieced together the data sent back by Voyager 2, they realized the frozen moon was geologically active. Geysers were spewing material into Triton's thin atmosphere.
Voyager discovered that the solar system is alive. The objects in the solar system have evolved and are continuing to evolve. And I think for a science team, that was a unique experience, which will be the highlight for many of the careers of the Voyager scientists.
The orbits and trajectories plotted for today's spacecraft continue to grow more complex as propulsion technology evolves and as the knowledge of paths of planets and their moons becomes more detailed. Scientists and engineers continue to build upon more than 60 years of experience.